The purpose of this video is to help you learn to find the pH of a weak acid solution. Recall that weak acids are soluble in water in that they are polar compounds, and they are proton donors, but they're not as good at their job as strong acids. They don't dissociate completely. Instead, only a few of the molecules will dissociate and donate a proton to the water, so instead of reacting to completion, weak acids set up equilibrium. These are really just a combination of acid problems and equilibrium problems. As a sample problem, we'll find what is the pH of a 1.5 molar solution of hypobromous acid. Because hypobromous acid is not on my list of 6 strong acids, I know that it's a weak acid. I can also tell that it's a weak acid because when I look in Appendix D, I find that hypobromous acid has a Ka value of 2.5 times 10 to the negative 9th. This Ka value pertains to the reaction hypobromous acid plus water, and I'm going to write that water is a liquid because it doesn't factor into the equilibrium expression, yields the hypobromous ion plus the hydronium ion. Whenever a question asks for the pH of a solution, what you're sneakily asking is, what is the concentration of the hydronium ion? Alright, I'm going to use an ice table since this is just an equilibrium problem. Get rid of the water since it's a liquid. My initial concentration of hypobromous acid is 1.5 molar. I don't have any of the hypobromite ion, and I'm going to say that the hydronium concentration in water is 0. That's kind of a little trick. There actually is hydronium in water, but we're going to ignore that. Minus x plus x plus x. The great thing about weak acid problems, it's always minus x plus x plus x. And at equilibrium, I'll have 1.5 minus x, 0 plus x, and 0 plus x as my concentrations. Alright, so let's solve this. We have that Ka is equal to, well, that's going to be the concentration of the hydronium ion times the concentration of the hypobromite ion over the concentration of hypobromous acid. And we know that all of that is equal to 2.5 times 10 to the negative 9th for this particular acid. Now we can simply go about solving this algebraically using values from our ice table. We have x times x over 1.5 minus x equals 2.5 times 10 to the negative 9th. You'll need to recall that since our K value is very, very small, that means that the amount of products at equilibrium will be very small, and the amount of hypobromous acid that actually dissociates is very small compared to 1.5. As a result, we can simplify this expression to x squared over 1.5. The question asks us to solve for the pH of this solution, and you'll recall that pH is simply the negative log of the hydronium ion concentration. So I'm essentially done with the problem. All I need to do now is solve for x, and when I do that, I get that x equals 6.12 times 10 to the negative 5th. I've kept an extra digit here, and this is equal to the hydronium ion concentration. When I take the negative logarithm of that number, I'll find that the pH of this solution is 4.21, and just a reminder, the 4 is telling us the power of 10. The 2, 1 are significant figures, so this has 2 significant figures. If I scroll back up to the original problem, you'll note 1.5 molar, and I have 2 significant figures in the value for Ka. One last thing I'd like to check. 6.12 times 10 to the negative 5th, that's the value we found for x, that's the amount of the hydronium ion formed. And we started with 1.5 molar hypobromous acid. So just quick note, this is the amount of dissociated ion, so that's the hydronium, over the concentration of the hypobromous acid. And when I do this and solve as a percent, I get 0.0041%. This is actually called the percent ionization, and if this number is less than 5%, we can say that our assumption that X was negligible is valid.